Okay, so we were talking about the various nanocomposites in aluminum based alloys. I have showed you some of the possibilities of these nanocomposites in this view graph, and most of these type of nanocomposites are made by two methods, either by rapid solidification processing or by mechanical alloying, because these are the two non-equilibrium processes which are easily available for most of the metallurgists. So mostly people use any of these two techniques. And when you talk in terms of FCC aluminum with some intermetallic components as nanoparticles precipitated in an aluminum matrix, this kind of phase can be easily obtained by first generating a supersaturated solid solution. For example, we know in every system there is a solubility limit at room temperature, beyond which under equilibrium conditions a precipitate is supposed to come out, and in most of the systems, particularly aluminum based systems, the solubility is very much restricted at room temperature. Even if you take aluminum copper also, the solubility at room temperature is very low, 0.5 or something like that, and in most of the other aluminum alloys it is very much restricted, and even the maximum solubility also is very small in many aluminum alloys. In copper it is about 5.6 we have seen, but if you look at many high temperature alloys, what I mean by high temperature alloys is most of the people know that aluminum copper alloys cannot be used at high temperatures. The moment you go to around 300 degrees or so, you have either precipitate coarsening or precipitate dissolution taking place, depending on the alloy composition that you are choosing. So as a result, you cannot really go to high temperatures in these. So what is the best way to go to high temperatures in aluminum alloys? To bring new alloys where the solute element has a very high melting point. One such examples are aluminum titanium alloys. People want to put elements such as titanium, okay, zirconium, hafnium, all these kind of elements, or even iron for that matter. Iron has a much higher melting point than copper. So if you put iron into aluminum, you can have the overall diffusivity of these alloying elements in the aluminum being very low, then precipitation coarsening is going to be very difficult, and precipitation dissolution is also going to be more difficult. As a result, you can have precipitates strengthening at to higher temperatures. One can improve what is called high temperature strength of these alloys by adding the alloying elements which have high melting points. So that was one of the basic alloy design criteria in developing newer aluminum alloys, and people have developed, for example, aluminum iron vanadium silicon alloy is one of the very popular alloy where people are all working on. So for example, iron, vanadium, silicon, all of them are high melting elements. So when you put them into aluminum and get precipitates out of this, for example, aluminum iron, you get Al3Fe, aluminum vanadium, again you have Al11V precipitates, and even Al3V also possible under some metastable conditions, and silicon anyway gives precipitation strengthening. I mean, silicon particles come out, so can give you strengthening. So like that, when you have this kind of alloy, people have been able to get much higher strengths. So all these kind of alloys can be melted, and in the liquid state we all know that all of them are soluble. So if you can have high solubility in the liquid state, so dissolve all these elements in the liquid state and then cool it rapidly, so that you get ultimately a supersaturated solid solution. Solutions having higher solute atoms dissolved in an aluminum, and now start doing edge hardening so that you can have precipitates, and that's how you can get this kind of intermetallics and produce intermetallics like that. One can also do it directly by rapid solidification by choosing a proper combination of cooling rates. For example, if you talk in terms of the CCT diagrams or TTT diagrams, for example, if you look at this, if you think of alpha aluminum as like this, and if you have another intermetallic compound like this, if you are taking a liquid aluminum and then cooling, you can choose a proper cooling rate. If you cool it very slowly, you may end up in alpha aluminum, because that is the easiest to nucleate in a aluminum alloy, because alpha aluminum is nothing but FCC aluminum. So, very easy to nucleate, and whereas intermetallic compounds to nucleate is much more difficult. So, but if you can have a cooling rate something like this, you can have a combination of aluminum. So, initially aluminum comes out, the remaining liquid which is there will come out as some of the intermetallic compound particles, so that you can have these particles distributed in an aluminum matrix. So, otherwise one can also cool it slightly slowly, get a supersaturated solid solution of aluminum and then precipitate it by aging. That also one can do it. And in addition, if one cools it very rapidly, get an amorphous phase and start crystallizing this amorphous phase. And when you crystallize this amorphous phase, depending on the composition that you choose, you can have various possibilities. For example, if the composition of the amorphous phase is exactly same as that of a compound which is possible in that system, you will see that amorphous phase transforms to the compound by what is called polymorphous crystallization. Okay. So, this is what is called polymorphous crystallization, where the composition remains the same. This is one type of crystallization process for the amorphous alloys, and that can lead to a number of intermetallic compounds depending on the alloy composition that you are choosing. And these compounds, if you can control the temperature and time of your aging treatment, you can have very fine precipitates of these intermetallics coming out and can give you what is called a nano composite with an amorphous matrix and intermetallics, nano intermetallics distributed in a amorphous matrix. And if you do the transformation complete, that amorphous matrix can finally transform to either alpha aluminum, or if it is a polymorphous transformation, completely all the amorphous phase transforms to a nano intermetallic. There will not be any composite here finally, it is only one single phase because it is a polymorphous crystallization. But all these grains of these intermetallics will be much finer, so that you can have fine intermetallic. But mostly people are not really happy with this kind of single phase microstructures. Nowadays most of the people do not want single phase microstructure, particularly single phase microstructures of intermetallics, because intermetallics are brittle. So everybody wants composites, nano composites, so that you can get the combination of both the high ductility of the matrix such as alpha aluminum and the high strength of the intermetallics, and they being very fine, you can have additional advantage of being a nanomaterial, so that you can have a good combination of strength and ductility. So that's the advantage of these nano composites. So everybody wants to go for that kind of composite. How do you get that? One possibility is what is called primary crystallization. That means if you choose your alloy composition such that what is given here, let us say alloy number 1, if you choose that alloy number 1. So the amorphous phase which is shown here, these are basically what we are drawing is free energy composition diagram. So the curve that is shown here is the free energy curve for amorphous phase, and the free energy curve for alpha aluminum, and the free energy curve for the intermetallic compound. That is what we have shown here. This intermetallic compound can be a crystalline or a quasi-crystalline. If it is a quasi-crystalline, then a quasi-crystal, nano quasi-crystal particles come out of the amorphous phase by polymorphous crystallization process. There are examples, for example, such as aluminum, copper, vanadium kind of alloys, where an amorphous material can be made by rapid solidification, and if you start heating it, the quasi-crystal will come out of that amorphous phase. And there are also examples such as aluminum, copper, iron, a number of such examples. There is also example I will show you is aluminum vanadium iron, mostly aluminum transition metal kind of systems. So if you choose aluminum transition metal kind of systems, you will have this kind of possibilities that if you cool it very rapidly, you get an amorphous phase and start heating it, because in these systems what I told you before are the Frank-Caspar phases. There are certain systems such as aluminum copper iron, aluminum copper vanadium, aluminum iron vanadium, these kind of systems, the Frank-Caspar phases do exist in the phase diagram, and because of which the possibility of formation of quasicrystalline phase is much easier in these alloys. So that is one possibility, either polymorphous crystallization to crystalline intermetallic compounds or polymorphous crystallization to quasicrystalline intermetallic compounds. Or if your alloy composition is slightly off the composition, you can have crystallization of these intermetallics or quasicrystals to give you what is called a nanocomposite, that you have an amorphous matrix into which you have a quasicrystalline particle or an intermetallic particle. If the composition is not exactly same as the intermetallic compound composition, but if the amorphous phase composition is slightly off, then you will not have 100% single phase intermetallic coming out, but you will have some amount of amorphous phase will be left out if the composition of the intermetallic and if the composition of the amorphous phase are not exactly the same. If they are exactly the same, then you can have perfect polymorphous crystallization taking place. If they are not the same, obviously mass balance cannot be maintained if you want to have 100% of the second phase coming out, because the composition is different. So that is one possibility. The second possibility is what is called primary crystallization, where you have amorphous alloy, its composition is close to that of the alpha aluminum composition, because of which alpha aluminum can easily nucleate from the amorphous matrix. So you will have an amorphous matrix into which an alpha aluminum may be dendrites of alpha aluminum or nanoparticles of alpha aluminum, depending on the nucleation rate that is available, which is a function of the undercooling that you are providing. So you can have this kind of possibility. This is possible either directly during rapid solidification, as I told you before, or you can have during the after the amorphous phase has formed, one can crystallize it. Okay, so this is what is called primary crystallization. And the other possibility is what is called eutectic crystallization. Primary crystallization, you have to remember one thing, that the moment the alpha aluminum comes out, you can see from this common tangent, the moment alpha aluminum comes out, you have to draw a tangent between alpha aluminum and an amorphous phase, because there is an amorphous phase which is here, this is the amorphous phase in which the alpha aluminum has come out, and we know the alpha aluminum composition is different from that of the amorphous phase, otherwise we do not call it as primary crystallization. What is the meaning of primary crystallization? The primary crystals that are coming out have a different composition that of the amorphous phase. This is similar to our for example, if you look at a hypoeutectic alloy solidifying, you take a hypoeutectic, what is the one that comes out first? That is the alpha phase. The alpha phase has a composition which is different from that of the liquid composition. So as a result, usually it is rich in the what is called the solvent. So if it is rich in the solvent, the liquid becomes richer in the solute, because the composition of the liquid will change. So you will have a mixture of alpha aluminum and liquid having a different composition than that of the alpha aluminum. This is what happens exactly if you look at the, let us say this is the composition that we are thinking. So this is the starting composition of that, and the starting alpha aluminum coming out will have a composition like this, and after you come to some lower temperature, you will see the alpha aluminum composition is this and the liquid composition is this. Why? Because the alpha, which is mostly rich in A atoms, has come out of the liquid. As a result, the liquid becomes richer in B atoms. all the A atoms are coming out of the liquid. So what happens is the A atoms get depleted in the liquid, so it becomes richer in B atoms. Exactly similarly here, if you take an amorphous phase from which an alpha aluminum comes out, that amorphous phase which is remaining will have a composition which is given by this common tangent. If you look at, this is the alpha aluminum composition, this is the remaining amorphous composition. So now you have a nanocomposite where an amorphous matrix is there whose composition is this, and an alpha aluminum whose composition is this. Okay, so you will have that kind of a situation, but that situation is not the lowest free energy situation, isn't it? Because the amorphous phase is never a stable phase. If you hold it for a long period, that amorphous phase has to transform to something. And usually in most of these systems there are certain intermetallic compounds do exist in the system, and the best and the lowest free energy situation is the combination of the alpha aluminum and the intermetallic compound. That is the lowest free energy. So as a result, you can see this phase further transforms. Initially by primary crystallization alpha aluminum can come out, and further if you hold it for longer period at higher temperature or at the same temperature for the longer period, ultimately the remaining amorphous phase whose composition is close to that of the intermetallic compound will give you that intermetallic compound. So that you will have now a combination of alpha aluminum plus the intermetallic compound. That is the final microstructure, and this microstructure can have a very fine precipitates of this intermetallic compound if you can control the nucleation rate of this, the temperature and time, if they are controlled properly, and if the composition is controlled properly, so that you can get a fine nanocomposite of alpha aluminum in and intermetallics. This is one possibility. The third possibility is directly the amorphous phase gives you a combination of alpha aluminum plus intermetallic. This is what is similar to a eutectic kind of reaction. Liquid gives you alpha plus some other second phase. So this is called eutectic crystallization. But eutectic crystallization has much higher activation barrier than either polymorphous crystallization or the primary crystallization, because two phases have to nucleate and interfacial energies of the two phases have to be considered. So usually eutectic crystallization is more difficult process. So these are all the various possibilities of crystallization, and that can lead to these kind of microstructures, a number of intermetallic compounds. Let us try to look at some examples. One such example is aluminum titanium alloys. Aluminum titanium alloys, particularly if you look at aluminum rich side of aluminum titanium alloys, on the aluminum rich side of aluminum titanium phase diagram you have one intermetallic compound called Al3Ti, which has about 75% atomic percent of aluminum and 25% of titanium in it, and this Al3Ti under equilibrium conditions has a structure which is like this DO22 structure, it is called the B crystal structure that you are seeing here. It is mostly, if you look at the first structure which is A, it is called L12 structure, which is nothing but the FCC type of structure, where all the body corners are occupied by one type of atoms and face centers are occupied by the another type of atom, and that is what is called L12 structure. And the DO22 is similar to L12, excepting that there are two such unit cells of this, and because of that you can see that you have an atom which belonging to the body corners. Atoms of one type of atoms are all at the body corners and the other type of atoms are all at the face centers, and that is what is called the DO22, and because of which the actual lattice, if you look at it, this whole thing is one unit cell, and because this whole thing is one unit cell, you will have the C axis much longer than the A axis, and that is what makes it a tetragonal type of structure. and this tetragonal structure makes the alloy more brittle. So the DO22 structure is more brittle than the L12 structure. So if you have Al3Ta particles with this DO22 structure in an aluminum matrix, you are not going to get very high ductility. The alloy is going to become brittle. So there is a lot of interest nowadays. Many people want to see how to make this Al3Ta into a cubic structure, because there is a lot of correlation between these two. So one can think of some possibilities by which one can make this kind of thing, and people have found out that if we can add certain ternary elements, we can stabilize the L12 type of structure. In fact, this kind of stabilization we know from steels, that we always add different alloying elements to stabilize either ferrite or austenite or carbides. All kinds of stabilizers we know, and we know that if you add certain alloying elements which have similar crystal structures that of the parent phase, there is a possibility of that particular structure being stabilized. So if you want austenite to be stabilized, you add some FCC elements. If you want ferrite to be stabilized, you add some BCC elements. Similarly, in some of these intermetallic compounds, if you add certain elements, for example, chromium, manganese, copper, nickel, these are all the elements which people know which can stabilize the L12 structure. So people try to add these elements and to see if they can be stabilized. A number of people have worked on this. But in addition, one can also, even without adding any element, if you do rapid solidification, one can get the L12 structure. Why? Because when you are rapidly solidifying, you are not providing sufficient time. So the phase that comes out will be that which has a similar crystal structure as that of the matrix phase. What is the matrix here? It is aluminum matrix. Aluminum is FCC. So the L12 phase, whose structure is similar to that of the FCC aluminum, that can easily come out than the DO22 structure, which is the body center tetragonal type of structure. So if you look at this various aluminum alloys with about 4% titanium and about 8% titanium, two different alloys have been shown here. One is an as-cast structure. If you look at the as-cast structure, you have nothing but aluminum peaks, and the peaks which are in between here, these are nothing but the DO22 Al3Ta peaks. And if you cool this alloy rapidly, you start getting a peak here, which is the L12 peak. L12 peak is FCC type of peak. So always you will have that peak very close to the FCC aluminum peaks. So you will have the FCC ordered FCC L12 peak always coming next to the FCC aluminum peaks, because it is also FCC, it will have similar peaks. So that is why you can see in this alloy, and particularly if you go to higher titanium, you will have more volume fraction of this phase coming out. That is why the peaks become more strong. So that is why you can see, if you take as cast, you will have only aluminum plus the BCT Al3Ta, but if you do melt spinning, you will have this phase. But you can still see some amount of DO22 still remains. Okay, so you cannot completely suppress at this particular cooling rates. Maybe if you go to much higher cooling rates, one can probably suppress this. Okay, or if you add certain alloying elements, possibly it is more easy. So people try to do various alloying elements. One such thing is chromium here. If you can look at this, if you take the as-cast alloys, as-cast means just make alloy without any rapid solidification. Just add these alloying elements to it, cast it, melt it and cast it under normal conditions. If you do it, you will see basically the alpha aluminum plus the DO22 Al3Ta, and some amount of, at higher chromium content, you will get aluminum chromium intermetallic compounds. And the same alloy, if it is cooled rapidly, you can see 0.5 chromium, 1 chromium and 2 chromium, different amounts of chromium is added into it, and you start seeing that this peak which is adjacent to this aluminum peak, and that peak is the Al3Ta L12 phase, and that peak amount keeps on increasing if you increase the copper content. And if you want to confirm this, you go to the TEM and one can look at these alloys, and these are basically the aluminum grains in which a small precipitates, more or less spherical precipitates of Al3 Ti L12 phase. How do you know it is L12? You can see this ordered reflections which are the faint small dots that you are seeing, which conform, and even in this also you can see the hexagonal arrangement of atoms in the lattice, these diffraction spots, and into which you see these faint spots here which tell you that it is the FCC ordered structure. Okay. So, one can look at these ordered reflections which are in, we know in X-ray also, whenever there is an ordered structure you get superlattice reflections, and superlattice reflections always have a lower intensity than the fundamental reflection. That is what exactly you are seeing here, and you can see nice spherical particles of the order of around 20 to 30 nanometer particles in an aluminum matrix, and this gives you strengths which are higher than the conventional aluminum alloys, particularly at higher temperatures. If you take a conventional 2017 type of alloy, which is aluminum copper alloy, it loses its strength rapidly as you increase the temperature, and whereas these alloys can retain the strength to a much higher temperature, basically because these Al3Ti particles do not dissolve back into the matrix. That is one interesting thing in these particles, that the solubility limit of titanium in aluminum, maximum solubility limit is very small if you look at the aluminum titanium phase diagram. So, because the maximum solubility limit is very small, the dissolution of these particles does not occur. In fact, even when you melt this alloy, the Al3Ti particles will remain in the liquid. So, you have that kind of a situation, that you have high melting intermetallic particles which do not dissolve back and which are in a nanocrystalline state, and which gives you much higher strength at high temperature. And you can also study at various temperature what happens as a function of time, and you can see the creep resistance of these alloys is very good. So, that even at long holding at high temperatures, 400 degrees also does not really reduce the strength to a large extent. So, that is one of the advantages of these alloys. And other type of nano composites could be, again I told you, titanium can be one addition, iron is another addition. You can add iron to make the alloying element, which is high melting alloying elements, added to aluminum to give you high strength at high temperatures. And one such thing is iron. When you add iron, different amounts of iron, what you see is that a new phase comes out, Al5Fe2 phase. In fact, this is not a equilibrium compound. Equilibrium compound usually is Al3Fe, and but Al3Fe phase, for it to come out is much more difficult from aluminum matrix. So, usually you see that this phase can easily come out because of lower activation barrier, and this is the phase which comes out when you take different amounts of iron and do what is called mechanical alloying. That means you take aluminum and iron powders together, put them in a mechanical ball mill, and then do mechanical alloying for various compositions. And interestingly, if you see at very small amount of iron, you get mostly aluminum peaks. What happens to iron? Yes, that aluminum, that iron goes into the solution and forms a solid solution basically, and it is so small that you cannot really see any precipitates coming out, and those precipitates cannot be detected because their volume fraction is very small. But as you keep on increasing this iron, you can see this first peak becomes smaller and smaller. What is the first peak? It is nothing but the first peak of aluminum. What is the first peak of aluminum? 111 peak. It is an FCC. So, 111 peak. What is the second peak? 200. And we always know that the second peak has a lower intensity than the first peak in most of the pure metals. So, as a result, you can see here, if you do pure aluminum also, you get a similar situation, that aluminum 111 will be more intense, aluminum 200, aluminum 220 will be still lower intense. But what you see here is, as I keep on increasing iron amount, this peak is decreasing, whereas this peak is increasing. So, the relative intensity of the 111 versus 200, 111 versus 200 peak, or in fact iron 110 peak also exists here near the 200 peak of that, and if you try to plot that, you can see that ratio keeps on decreasing, and that is because you get a new phase here, and that is the Al5Fe2 phase, whose peak position is exactly same as the aluminum 200, that you cannot really detect it separately, but from this fact that the aluminum 111 peak is decreasing. If the aluminum 111 peak is decreasing, then aluminum 200 peak also should correspondingly decrease, but you see the aluminum 200 peak is bigger now. That is because there is another phase that has come out, and that is overlapping with that, and from that you can make out that the actual aluminum phase has come down and the amount of precipitate has gone up. So here basically you have a kind of a nano composite, and from the peak broadening one can clearly see that you have a very fine crystallite size, and one can calculate the lattice parameters of all these, and then show that if you take the aluminum 20% iron, there is a lattice parameter increase as a function of milling time. That is basically because of the formation of Al5Fe2, whereas in all other cases where you have a solid solution formation, there is a continuous decrease in the lattice parameter of aluminum, because when you take iron is slightly a smaller atom size when compared to aluminum. So when you put iron into aluminum, the lattice parameter decreases because the atomic size decreases. So whereas here suddenly you start seeing that when you put 20%, you can see much bigger. This is because of the second phase that is coming out. Okay, and one can also plot as a function of composition what is the lattice parameter, and you can see up to 10% there is a continuous decrease in the lattice parameter, and then you start seeing that there is an increase, and this is because of the formation of those precipitate which does not form up to here, and beyond 10% you start seeing the formation of that precipitate, and that precipitate is what gives you the increase in the lattice parameter. And one can talk how the lattice parameter changes as a function of crystal size, and one can clearly see that up to a certain crystallite size there is no increase in the lattice parameter. That means the solubility does not increase up to a certain crystallite size. Once you go below a certain crystallite size, let us say below about 20 nanometers or so, then suddenly you start seeing that the lattice parameter starts increasing. Lattice parameter starts increasing means the solubility is increasing, more and more solubility taking place, and that is what exactly you see here. And this one can also talk in terms of crystallite size, how the crystallite size is changing, and simultaneously the lattice parameter increasing. So you can see crystallite size keeps on, as crystallite size keeps on dropping down, the lattice parameter keeps on increasing. So there is a strong correlation between crystallite size and the lattice parameter, or crystallite size versus solubility. Okay, and one can also show that these nanocomposites have much higher strength, and that is what you see here. These are green compacts of aluminum iron kind of alloy with about different amounts of iron shown here, and the green densities are of the order of around 75% to 85% here for various compositions. And you can see here pure aluminum and pure iron green densities are also shown here, which are much higher than this. This is basically because when you add some iron to aluminum, there is some strain that is generated because of solid solution hardening, and because of the strain the compacts will not have higher density. Whenever you have the strain inside the lattice, compaction is more difficult. So that is why one has to heat these powders to certain extent so that the strain can be relieved, and then you can have much better densities. So that is why you can see pure metals, you can have much higher densification than the alloys. And if you look at how the hardness of this changes, you can see the hardness can reach almost 2 gigapascals. So you can have hardness, Vickers hardness is also shown here, and that is converted into stress equivalents of that which shows you about 2 gigapascals, which is much higher than any normal aluminum. For example, pure aluminum you get only this much, pure iron you get this much, and you can see what you get for an aluminum iron alloy is much better than both of them, and that is basically because of the nano precipitates of this Al5Fe2 which is coming out in an aluminum matrix. Okay. So, this is the story of aluminum iron. One can also produce intermetallics, nanocrystalline intermetallics in an aluminum alloys. One such thing is what are called aluminides. Lot of people are working on these aluminides. Aluminides are nothing but intermetallics containing aluminum. There are basically 3 classes of aluminides which people have studied to a large extent. One is called nickel aluminides, second is iron aluminides, third is titanium aluminides. The most popular aluminides in this series is, for example, in the nickel aluminide series you have either Al3Ni or AlNi or NiAl, people can anything you can call it, or Ni3Al. These are the most important compounds in this system. Similarly, in the iron also you can have Al3Fe or AlFe or Fe3Al. Same thing true for titanium. You can have Al3Ti, you can have Alti or TiAl or Ti3Al. These compounds have become very popular. Among all these, particularly the aluminum rich compositions, that means not the third compound, the first 2 are more interesting. Why? Because of lower density. Higher aluminum means lower density, and because it is lower density you can have high specific strength. So, for example, Al3Fe, Al3Ti, Al3Ni or AlNi, AlFe, Ti, these are much more popular than these alloys, and all of them have high melting points, high strengths, and can give you good strengthening in these aluminum matrix. So, if you can have these particles either as single phase particles or particularly in an aluminum matrix, if you can put these particles, that is what we have shown. One example as Al3Ta, as one example Al3Fe, another example I have shown you, and this is single phase intermetallics. A number of people have studied on how to make single phase aluminides. There are many people who have studied, for example, Ni3Al. We know that Ni3Al, if you can have in a nickel matrix, you can have much higher strength. That is what is nickel based superalloy. So, people thought, why should I put it in nickel base? I make Ni3Al separately as a single phase Ni3Al. People have made single phase Ni3Al which has a much higher melting point than a nickel based superalloy having Ni3Al particles, and obviously if you have a high melting point, creep resistance is much higher. So, people wanted to try that, and if you have a single phase, there are no phase boundaries. If there are no phase boundaries, creep problem is also restricted. So, people have tried single phase Ni3Al, and they made turbine blades using single phase Ni3Al. Number of people have, for example, Inco is a company, international nickel company, has made single phase Ni3Al, but the problem was they were quite brittle, and people tried to avoid that, overcome that problem also by adding something. Do you know? No, boron. Boron is a wonder element which when added to the Ni3Al by small amounts, just 0.1% or so, can give you tremendously improved toughening. That is basically because boron is a very small element, goes to the grain boundaries and improves cohesion at the grain boundaries, and improves the what is called the transgranular cracking instead of the intergranular cracking, and because of which you get much higher toughening. So, people have studied boron, what is called ductilization of Ni3Al by boron. A lot of people have studied. So, these are intermetallics, but conventional procedure of making this intermetallics is by the normal liquid metallurgy route. That means you take aluminum and nickel, melt them together and make the casting. But if you want to do that, many of the aluminates you have two problems. One problem is their melting points are very high. If the melting point is very high, obviously you need high temperature furnaces to melt these alloys, and then there is a lot of power consumption involved in that. And whether really you can have the furnaces which can withstand that high temperatures is a problem. Most of them have melting points of the order of 1600, 1700 degrees centigrade, very high melting points. So that is one problem. Second problem is that the melting point difference between the two elements here is very large. If I look at titanium aluminates or nickel aluminates or iron aluminates, the melting point difference between the iron and aluminum, titanium and aluminum, nickel and aluminum is very large. Aluminum is 660, whereas nickel melts around 1500, 1450 or so. And as a result, such a high difference in the melting point, when you are trying to melt the two elements together, there is a possibility of some vaporization of aluminum before the nickel melts. So you have a lot of problem of loss of aluminum. So yes, we will stop here.